In this video, we will be looking at how three planes can intersect, if they intersect at all. So there are a few things that we have to check for to conclude what scenario we're in. We need to check the normals, and we need to check the full equations themselves. When we're checking the normals, we're checking to see if the normals are collinear, meaning the planes are parallel, and checking to see if the normals are coplanar, meaning the normals lie in the exact same plane. Then we also want to check the equations of the three planes to see if any of them are coincident, meaning you can multiply one equation by a scalar multiple fully to get the other equation. Once you check these things, then you can conclude what scenario you're in, because we actually have 8 different scenarios of how three planes can interact. So let's take a look. First is when we have a consistent system, meaning there is some sort of common intersection, whether it's a single point, a single line, or the whole plane itself. So scenario number 1 is we have a point of intersection. And the only time you're going to have a point of intersection is when the normals are not collinear and not coplanar. So there is no connection between those normals. And if that happens, the intersection is at a single point. And we would solve with elimination or substitution. Next, three planes can intersect at a single line. So there's an infinite number of solutions, any point on that line. And the way you check for a line of intersection is if the normals are coplanar. They're not collinear, so the planes are clearly not parallel to each other, but all of the normals of these three planes would be coplanar. And remember, the normals are the lines that are perpendicular to that plane. So let's say this is the normal perpendicular to that. This is the normal perpendicular to that. This is the normal perpendicular to that plane. And all three of those normals belong in the same plane. Next, there's another way to have a line of intersection, and that's when two of the planes are coincident, so they're the exact same, meaning the normals are collinear, and you can just multiply one equation by a number to get the other equation. And then your third plane will just pass right through. Now this ends up looking like a two-plane scenario. That's how we would solve it, because two of the planes are already the exact same. And if you look at all three normals will be coplanar. The final consistent system scenario is when there is a full plane of intersection, and that's when all three planes are coincident. So if you were to look at the normals, they're collinear because the planes are parallel, and they're coplanar because all the normals would be parallel, which means all those normals would be in the exact same plane. Now, we also have 4 inconsistent systems, and that's when there is no common intersection. The first scenario is when your three planes will form a triangular prism out of those individual lines of intersection. So if you see, each plane will intersect with the other one at a line, and then you have this triangular prism formed. Now if you check the normals are going to be coplanar, so all three of these normals coming out of the planes will be coplanar, but they're not collinear because clearly the planes are not parallel. We can also have two parallel planes that are also distinct. Okay, so like this, which means there's no way for a common intersection. Each of these parallel planes will intersect with the other, but all three together have nothing in common. And you'll notice that two of the normals are going to be collinear, and then all three would be coplanar. You can have all three planes being parallel and distinct, so absolutely no intersection here. All the normals will be collinear. And actually, if you look at the equations themselves, you can multiply the equations by a number to get the other coefficients of x, y, z. It will not apply to the constant. And finally, you might have two coincident and then one parallel and distinct plane. So all the normals will be collinear again because they're all parallel, but specifically two of the planes, you'll be able to multiply one equation fully by a scalar to get the other. So let's try this out with our first example. So we're going to start off by checking out those normals. So I'm going to list out all my normals. 1, -3, -2, 2, -5, 1, and -3, 6, 2. So I'm going to look at all three of the normals, look at them in pairs, look at them all together, and they're not collinear. None of them. Which means they're not parallel. Now I have to check to see if they're coplanar, to see if maybe there's a line of intersection. So as a reminder, we check to see if our planes are coplanar by doing a dot product and a cross product. But of course, in order for this to be meaningful, we need to do a cross product first. So I'm going to do the cross product between the second and the third normal. And I'll just write that out on the side here. So -5, 1, 2, -5, 6, 2, -3, 6. So -10 minus 6. Well, actually, I'll write my first normal. Dot. Okay, -10 minus 6 is -16. -3 minus 4 is -7. 12 minus 15 is -3. And now we can go ahead and do that dot product. So that's going to be -16 plus 21 plus 6, which is -11. So not coplanar. So with the fact that the normals are not collinear, not coplanar, that means we're going to have a point of intersection. So let's get to the solving. So I'm going to look at my planes here, and I'm going to start off by eliminating the x's. That's what I'm choosing to do. So I'm going to double plane 1 and subtract plane 2. And I'm just organizing my work here. So if someone were to look at my work, they know which planes I'm taking and what I'm trying to eliminate. So we're going to subtract our lines. So the x's are gone. We have -1y, we have -5z, and we have -21. So first, x is eliminated. Now I'm going to eliminate x again so that I have two equations in terms of y and z. To do that, I'm going to triple plane 1 this time and add it to plane 3. Okay, so we're going to add here. So the x's are gone again. Then we have -3y, -4z, and -19. Now I can look at these two linear equations. And now we have two equations, two unknowns, so one more elimination here. And I'm just going to triple this equation. And I'm going to write it out right here. So -3y, -15z, and -63. And now subtraction will do the trick. So the y's are gone. We have 11z, and we have 44. And if we divide by 11, the z component of the point of intersection is 4. Now I can slowly bring this value into the other equations to get my other variables. So I'm going to plug z into this equation here. -y minus 5 times 4 equals -21. So -y minus 20 is negative 21. I'm going to do a swap this way so that the y is positive, and then I have negative 20 plus 21. So y is 1. And now I'll take y is 1 and z equals 4, and I'm going to plug it into plane 1 to solve for x. So we're going to have x minus 3 times 1 minus 2 times 4 equals negative 9. So that's negative 3 minus 8, and bring that over. So negative 9 plus 11, which is 2. So there we are, x is 2. Therefore, the point of intersection is 2, 1, 4. And you could always do a left side, right side check by checking these values in plane 2 and plane 3. I know plane 1 works because that's where I got x from. All right, next example. All right, so we're going to start off by looking at the normals. And before I even write them out, I actually noticed something about the planes themselves. So it looks like I can take plane 1 fully and multiply by 2 to get plane 2. So that means plane 1 and 2 are coincident. But then also, I can take plane 1 and multiply it by negative 4 to get plane 3. Or I can even take the second plane and multiply it by negative 2 to get plane 3. So the fact that all 3 of these planes are connected in some form with a scalar multiple fully, that means the planes are coincident. All 3 of them, which means there's an infinite number of solutions, and the solution is any point on the plane. So there are an infinite number of solutions. Any point on, I'm just going to pick the most simple equation, is a point of intersection. There we are. That one's quick and easy. Now, let's say I actually neglected looking at my normals and I tried to solve for the point of intersection and I did elimination. Let's say I doubled this equation. These would match right away, and if I subtracted my lines, everything would disappear and I would end up with 0 equals 0. It's a true statement telling me there is a solution and it's an infinite number of solutions. And then I could do it with another one and notice, oh, those are also the exact same, and go from there. But this is definitely the quickest and probably the best way to visualize what scenario you're in. All right, for the next one. I don't see a full connection here between any of the planes, so I'm going to go to checking my normals. So 2, 1, 1. 1, 3, negative 2, 3, 2, 1. Yeah, these are not collinear. So they're not parallel. So now I can check for coplanar. So again, I'm going to do the same thing. I'm going to do the dot product between the first normal with the cross product of normals 2 and 3. So for the cross product, we have 3 minus negative 4, negative 6 minus 1, 2 minus 9. And now that's 14 minus 7 minus 7, that's 0. These are coplanar, but they're not collinear. So nothing is parallel here, but all the normals are coplanar. This means we either have a common line of intersection between all three planes, so it looks like that revolving door scenario, or we have an inconsistent system where the three planes form a triangular prism and there is no common line of intersection. Each pair of planes just has a line of intersection, but nothing common among all three. So we actually have to do our elimination here to see what we're going to end up with. So it's going to start the same as with a point of intersection. I'm going to start with elimination here. And I'm going to choose to eliminate the z's this time. It looks a little easier. So I'm going to start off with plane 1 and plane 3 and just subtracting them. So now we have negative x minus y equals 3. And I'm going to eliminate z again. This time I'm going to use double plane 1 and I'm going to add it to plane 2. That's 4x plus 2y plus 2z equals 0. And x plus 3y minus 2z equals negative 15. We're going to add everything. And we have 5x plus 5y, z's are gone, equals negative 15. I'm going to multiply this one by 5. And you might already notice here that if I add these lines, everything disappears. The x's are gone, the y's are gone, so left side is 0. Negative plus 15 is 0. This is a true statement, which means we have a consistent system. So it must be a line of intersection, not that triangular prism setup. So now we can go on our way to solve for a line. And because we know it's a line, our equation will have a parameter. We're going to get a vector equation. So I'm going to go back to this equation here. And I'm going to say, let x equal t. So then I have negative t minus y equals 3. I'm going to do some swapping here so that y is equal to negative 3 minus t. There's the second parametric equation that we have. And now I can take both of these and sub them into one of the planes. I'm going to go into plane 1 and replace x with t and y with negative 3 minus t. So that's going to be 2t for 2x minus 3 minus t, because it just said plus y, plus z equals 0. So bring the negative 3 over, it turns positive. 2t minus t is just 1t, it moves over, and it is negative. So there we are. So therefore, the line of intersection is, I'm going to write my vector equation here. So starting with vector r naught, which comes from the constants, 0 for x, negative 3 for y, 3 for z, plus t times the direction vector. So 1, negative 1, negative 1, where t is an element of all real numbers. There we are. Next one. So when I look at this next system, I notice there is a connection between those coefficients of x, y, z, but not so much with the constants. For example, if I take x, 2y, and 3z and multiply them by 2, so pretty much if I multiply the normal by 2, I will get the second normal. But if I try to do the same thing with the constants, I don't. So 2 times the first plane will not give me the second planes, which means plane 1 and plane 2 are parallel and distinct. Let's bring plane 3 into the mix. Well, it looks like I can take that first normal and just multiply it by negative 1 to get the third normal. So that means they're parallel. But if I try to take the constant and multiply it by negative 1, so if I look at 1, I should get negative 1 for the constant in plane 3, but I don't. So that means all 3 planes are parallel and distinct. So there is no intersection. There's no common intersection, but also no intersection among pairs of planes either, because they're all parallel and distinct. So that's a quick one to do. So in this next setup, if I am looking at my normals and my equations, I feel like there's a connection between plane 2 and 3, because I can take plane 2 and double it, and I'll get plane 3. But plane 1 has nothing to do with this. So 2 planes are coincident. This one has a normal of 1, 1, negative 1, which has nothing to do with the normals 1, negative 2, 1, as in plane 2. Not connected to others. And I mean, the minute I see this, I don't really have to test to see if they're coplanar. If I have 2 planes that are coincident and one that's not, there has to be a line of intersection here, because now it just looks like a 2-plane setup. I can solve this just using plane 1 and plane 2, because at the end of the day, plane 3 is the same as plane 2. So I don't even need this at all. So once I'm there, I'm back to a 2-plane setup. And let's get that line of intersection. Okay, so I'm going to start off by eliminating the x's, and the x's already match, so I'm just going to subtract those lines, and I'll just subtract them from the way they're already set up. So x minus x is gone, y minus negative 2y is 3y, negative z minus z is negative 2z, and 2 minus 4 is negative 2. And now I know there's a line of intersection, so I'm just going to say let y equal t. There's my first parameter. So I have 3t minus 2z equals negative 2. And I'm going to isolate for z here. So 3t plus 2 equals 2z. And 3 over 2t plus 1 equals z. Okay. Now I'm going to sub both of these. I'm going to sub them into plane 1. So that's going to be x plus t minus 3 over 2t plus 1 equals 2. Distribute that negative in. And now isolate. So when the 1 moves over, it's positive, so 2 plus 1. T minus 3 over 2t is negative a half t, so when it moves over, it'll be positive. So there are my 3 parametric equations. So therefore, the line of intersection is vector r equals, so vector r not coming from the constants, 3, 0, 1 plus t times the direction vector, so a half, 1, 3 over 2. And if you don't want your direction vector to have those fractions, you can just get a collinear vector, so you can multiply all of these by 2 and then have the direction vector 1, 2, and 3. And there we are. Next example. So if I look at my first 2 planes, I can multiply the first plane by 3 and get the second plane fully. So these 2 planes must be coincident. They're right on top of each other. But then if I look at plane 3, I have a connection with the normals. So for example, I can take the first normal and multiply it by negative 2 to get the third normal. But that doesn't apply to the constant. So if I try to do negative 2 times plane 1, I'm not going to get plane 3. So plane 3 is parallel and distinct from plane 1 and plane 2, because those ones are coincident. So what we have here is one plane here, and then two planes that are on top of each other here. So there is no common intersection. Plane 1 and plane 2 have an infinite number of points of intersection, but all three together have nothing in common. Next. So just looking at the equations themselves, I don't really see a connection anywhere, but I'll write out my normals. So first two definitely not connected. The third one had potential with the second, but the signs messed it up. So none of them are collinear, meaning also not parallel. So let's check for coplanar. So the dot product between the first normal with the cross product of the second and third. So we're going to have 2, 1, 1 dot 1 minus 1 is 0, 1 minus negative 1 is 2, negative 1 minus 1 is negative 2. So that'll be 0 plus 2 minus 2 equals 0. So we do have a coplanar set of normals, which means we either have that revolving door and we will have a line of intersection like we did in one of the examples, or we'll have that triangular prism set up where it's an inconsistent system. There are no intersections there. So let's see what happens. We're going to start this off with regular elimination, and I'm going to eliminate the x's. So I'll start off by adding plane 2 and plane 3. And they're already nicely lined up here, so I'm just going to add them from there. Negative x plus x is 0, y plus y is 2y, z plus z is 2z, negative 1 plus 0 is negative 1. And then I'll do plane 1, and I'll double plane 2 so I can add them. Okay, so 2x plus negative 2x is gone, y plus 2y, z plus 2z, 1 plus negative 2 is negative 1. All right, now I'll triple this one and double this one. So that's going to be 6y plus 6z equals negative 3, and then 6y plus 6z equals negative 2. You can probably already see this. If we subtract, the y's and the z's will cancel out, which I was expecting, but then negative 3 minus negative 2 is negative 1. That is not a true statement. This is an inconsistent system. So there is no common intersection, which means this must be the triangular prism setup. So therefore, there is no intersection. And notice for all of these examples, if there is no intersection, I am concluding what the setup is. I'm not just going straight to no intersection. There's no intersection because the planes are arranged in that triangular prism. There is nothing common among all three planes. All right, final example here. Let's look at our normals. 1, 1, negative 1, 1, 1, 1. So no connection there because of that sign that's messing everything up. And then negative 2, and positive 2. All right, so looking at this, the first normal and the third one, if I take the first normal and multiply it by negative 2, I'll get the third one. And if I try to do that with the constants as well, so negative 2 times that first plane, I will not get the third plane. So plane 1 and plane 3 are parallel and distinct. The second normal has no connection to the other ones. So you have two planes that are parallel and distinct. So maybe like this. The third one's not connected, so it would pass through let's say, like this, and you'll have individual lines of intersection, but nothing actually common as a whole for all three. And that's it for how three planes can interact. And we saw each of the 8 scenarios in our examples. So make sure you're always checking the normals first to see if they're collinear. Check to see if the equations themselves can be fully multiplied by a scalar to get another one, to check for coincident planes. Check to see if your normals are coplanar, because that will really narrow down what scenario you're in, and that can either guide you to not solve at all or to see whether you're solving for a point of intersection or a line of intersection, or if it's the whole plane itself that is intersecting.